Okay, so this lecture is for Quality Lab Skills 1, and it talks about the difference between pH and titratable acidity. So essentially, we sort of use them for the same purposes, but they're not identical. We talked last week about titratable acidity being the total acids in a solution or in a product. So in this case, milk. So not just the free hydrogen ions, but all the bound acids that are inherent to the milk. And then pH strictly measures the concentration of hydrogen ions. So if there's a large concentration of hydrogen ions, what's the pH going to be? Low or high? Is it? It'll be low because it's an inverse relationship. If there's not many hydrogen ions, what's the pH going to be? High. It's going to be a base. So that, if you're having trouble with that concept, make sure you diagram that out. And I can put a diagram on the board to help you also. So again, the reason they want to know titratable acidity is for a couple reasons. The acid in a product can impact the flavor. So for instance, something that's really acidic like a lemon, what's the flavor like? It's sour. And then other things like proteins, phosphates, citrates, or carbon dioxide can impact TA. So it actually masquerades as an acid in the reaction. So there may be other things that are off in the product or raw material based on the TA results. So you can measure pH, but they also like to measure titratable acidity. Again, pH is a function of 10 numbers of the hydrogen ions. So however many hydrogen ions as a log of 10, and don't worry about that right now. But pH does influence the physical properties of the cheese. If it's real acidic or not acidic enough, the texture will be different, the flavor will be different, it won't coagulate correctly. Again, this slide is just reiterating that the more hydrogen ions there are, the more it's more acidic, and vice versa. When you see the words molar and normal, so M and N capitalized, that's a measure of concentration. Have you guys started talking about that in fundamentals of chemistry yet? Concentration? No? You'll get there. And it's logarithmic, so that means it's a power of 10. So it's a negative log, so like pH of 1 is the hydrogen ions to the power of negative 10. So it becomes really confusing, so we just convert it to numbers. So for instance, 0.00001 is 10 to the minus 6, but that's actually a pH of 6. Because it's below the decimal point, that's why the log is negative. Does that make sense? So you all know what 10 squared is, right? That's 100. Uh-oh. Bless you. So anyway, so this just explains how this guy, Sorensen, who decided to be a pH expert, said that he wants to convert it. So it's just actually a number instead of writing 10 to the minus 6, 10 to the minus 7, whatever. So here's the pH scale that I wanted to show you that goes from 0 to 14. But you can see there kind of where everything's at. So battery acid, sulfuric acid, those are all down on the scale. Like they're way down here between the 1 and the 4. So there is acidic as tomato juice, orange juice, lemon juice, and gastric acid. But these are more of a weak acid. They're weaker, so they have more conjugated or citric acids in them, so they don't burn as hard or fast as like battery acid, because that's just a straight strong acid. That's like 1 hydrogen and 1 chloride, so it's pretty much stronger. But people can drink lemon juice without ruining their face, right? Even though it's a strong acid. Your stomach acid is right in here, I think between the 3 and the 4. So you can see urine is a little bit acidic. That's to kind of help control the bacteria. Seawater is a little bit basic. And as you go up, all those bases can combine They're used a lot of times for antacids to kind of neutralize stomach acid, like the milk of magnesia. I'm going to end this quick. That was really